We are live on YouTube. I think we can start.
All right, let's start then. Welcome everyone to second Discord session. My name is Dejan. I'm a developer advocate here at RavenDB. Thanks to my colleagues, we are streaming again. And the topic this evening will be how to implement AI search in your applications. So we are all fed up with AI and everyone is talking about it, but I would like to take a different turn. I would like to actually show you how to solve some real serious problems. And from that perspective, AI is a great tool for solving problems. Furthermore, if you're forced for any reason to add any kind of AI in your application, this could be a good solution, what I'm going to be speaking about this evening. So, searching. Probably as long as we have computers and information, we need to perform some kind of searching. And here on this slide, you can see a brief evolution of how searching was developing. We can start with very, let's call it naive or primitive way of searching or matching information. That would be exact matching. So with exact matching, you would like to locate the word within a text and you supply your word and it is exactly compared to other words. When you run or when algorithm runs into something that's exactly matching, you will get it back. And you can already assume or you can already see why this is not a good idea. So imagine car with the capital C and the car with lowercase c, they will not match. So of course, to improve on that and to improve on exact and partial matching, we move into area where we can introduce so-called wildcards. So partial matching is now available where you can, for example, specify a prefix and a word with a prefix will be matched. So in my example here, we have a car and carpet. And of course, this is not too good of a match because car and carpet are like JavaScript and Java, not much related. But we are now slightly better. We are widening the scope of the results. So if we specify car with wildcard, we will get multiple matching results. So slightly better. And finally, we are reaching something that most of the applications are using today. If you're familiar with Lucene, if you're familiar with RavenDB, you're probably already using this. So you can see a sentence here, my car is red. And let's imagine I would like to perform full text search for word car. So what will happen inside of full text search engines like Lucene? Well, every such sentence or piece of text will be taken. It will be processed. So what will happen first? My car is red consists of 4 words. This sentence will be split into individual words on the boundaries of interpunction, comma, full stop, space, etc., etc. So we will get 4 words. Then some kind of transformations will be applied. So for example, all words will be lowercase. So you can see that my with capital M in the sentence on the left is transformed into my with lowercase m in the collection of the words. And then some so-called stop words will be eliminated. Stop words are very common words. In English, this is. The would be another example. These words are not carrying any, let's say, useful information. No one will search for is or the. So in most analyzers, such words will be eliminated. So as you can see, through the series of transformations, sentence my car is red will be transformed into the array of 3 words, my car and word red. And then what I typed in, word car, will be matched against these words. And of course, if I typed CAR with capital C, car with capital C, my input would also be transformed before matching is implemented. So what's important to understand here is that, again, a result I'm getting is good, but there was some processing needed before I was able to get my results. And this, when you put all the knowledge on one pile, knowledge that was needed to implement it, something like this, it's not trivial. It's essentially lots of research and work and implementation, and results are great because I'm able to, with high accuracy, perform partial matching of one word against whole sentence, get my results with low latency, and life is good. But all of these methods of matching or searching are relying on syntax. So comparing letters and words one against the other. And semantical matching would be step forward, and this is what I'm going to be speaking about today. So if I type red car using full text search matching, I will get my car is red sentence, but I will not get a Ferrari. To return Ferrari for the input term signature red car, you could almost say some understanding is needed, or we are now expecting computer or algorithm or machine to understand what do we mean by signature red car. And this is quite interesting because even a small kid would understand something like this, but it's rather challenging to train computers to start returning results this good. So how to implement something like this? And this is a technique that is older than current AI hype. So this is great. This means that this is something tested, tried out, and it's actually working with high accuracy. And answer to how to implement it would be similar to a joke of how to put elephant in the refrigerator. Well, in 3 easy steps. You open the refrigerator, you put the elephant in, and you close the door of the refrigerator. So I would take a phrase, first phrase, and convert it to some kind of numerical representation. Do the same with phrase number 2, convert it to some numbers or numerical representation, and then I would compare these two numerical representations for phrase 1 and phrase 2 and compute distance between them. And the closer they are, the more similar phrases are. So we managed to do in this case, or we intend to do what is common approach in mathematics. We take a problem in one area, we translate it to another area and operate in this area where it's easier for us. And when we are programming, it's definitely easier to work with numbers, with numerical values than attempting to do a semantical, meaningful similarity. So how to put that elephant in the fridge? Well, it turns out technique is rather simple. So let's imagine I would like to represent semantical meaning of the phrase beach towel. One possible approach would be to quantify probabilities that this phrase is conforming to some attributes. Or to turn things around, here I came with some attributes, words beach, sun, water, sand, etc., etc. And in the end, I have snow and winter. And now I'm taking the beach towel as a term, and I'm trying to determine how good or how precise each of these attributes is describing beach towel. And of course, if I start with beach, 91% could be some kind of measurement of how beach towel is applicable, or the attribute beach is applicable to beach towel. So we have a very high correlation, and also when you start thinking about it, what we think about when I mention beach towel, we think about a sea, sun, sand, swimming, vacation, summer, waves, maybe surfing. So these numbers in the right column are actually numbers between 0 and 1. And you can also look at them as percentages. So 0.91 for beach is actually 91% of correlation between attribute beach and beach towel. So it's not complex, it's rather simple. We are determining for each one of these attributes how applicable it is to our beach towel. And then I can also take something like sunglasses and apply the same technique. I'm taking fixed number of these attributes. And again, I'm trying to quantify how well each of these attributes is applicable to my term. And if you look, you can see some differences. For example, beach towel, I think that beach towel is more related to beach than the sunglasses. If you go down the a list of these attributes, you can of course see something interesting that if you go and look at skiing, for example, I put 16% of correlation between beach towel and skiing, but I have 38% between sunglasses and skiing, because when you're skiing, sun can be very strong and you need some kind of protection. For that reason, I'm also having here a slightly stronger correlation between snow and sunglasses, 34%, than between snow and beach towel. So as you can see, technique is rather simple and straightforward, and we can also go and outsource this so someone do this for us. And you can already guess that the more attributes I have, the more precise I will be able to quantify characteristics of a specific object I'm speaking about. And now when we have these numbers, how to determine similarity? How can we determine if beach towel and sunglasses are close to each other by their actual semantical meaning? And now we are reaching to the very origins of the term vector embeddings. So these numbers can be put into the, for programmers, they can be put into the array of numbers, which you can see on the screen. But if we are operating in mathematical realm, we could also say that these are the vectors, because these numbers that you can see on the screen could also represent a point in n-dimensional space. So looking here, what we have here is around 20 attributes. So if you put all of these attributes into the array, these could be coordinates of a dot in a 20-dimensional space. And now if we connect 0 origin point in the coordinate system, and we draw a line to the point that 20 numbers represent, we are getting to vectors, as you can see on the screen. And then we can use simple mathematical operation of computing cosine similarity to compute how far away or how close these two vectors are. So the more inline these two vectors and the similar length they have, the more similar length they have, they will be closer. So when we compute cosine similarity, it can relate to 0, which is orthogonal vectors, completely unrelated, or they can be overlapping each other, which would be perfect similarity. They are going into exact same direction with same intensity. And again, this number between 0 and 1 could be looked upon as probability in percentages from 0% to 100% similarity. So rather simple mathematical operation that can be highly efficiently computed, especially today when CPUs are supporting vector operations directly. So very efficient. And of course, every good programmer is a lazy one. And of course, it's natural that we people want to optimize things and automate it. So how to do it? Well, this is where AI part comes into play. So as I mentioned, vector search, vector comparison, vector embeddings are much, much older than current AI hype. One of the earliest such attempts was a so-called text embedding model by Google, applied on Google News project. It's called Word to Vec. So solutions which are accepting either sentences or words or phrases and computing these numbers, these vectors of numbers, are called text embedding models. And please pay attention, when I was learning all of this, I was frequently mixing up text embedding models and large language models. They are completely different things used for different purposes. Of course, LLM is behind solutions like ChatGPT. Here we are speaking about text embedding models, solutions that will accept phrase and will respond back by the array of numbers or vector of numbers. And as you can see on this slide, these are just some models that were developed in the very beginning, like FastText from Facebook. And today we have some models coming from OpenAI. OpenAI Ada V2 was one of the earliest coming from OpenAI. What is, however, interesting and important is how many numbers, float numbers, are returned by text embedding model. So starting with the earliest ones, which were returning 300 numbers, now we are going into a couple of thousand of dimensions with such vectors. And this is important because the more numbers we have, the more precise semantical meaning of each phrase is encoded. Also, what is interesting is that we will not get back something like this. We will not get back attributes and numbers. What text embedding model will return to us is just a set of numbers. And actually, we have no idea what these numbers represent. That's the magic of the AI that is happening behind the scene. But what we do know is that each of these models is consistent, and it will consistently produce a faithful numerical representation of the meaning of the phrases that we are sending. And in version 7 that was out this year, RavenDB started supporting vector search, which is quite interesting because RavenDB is not a specialized solution. RavenDB is not a specialized vector database. It's a general purpose database, but now you have one more tool at your disposal to use in your application. And I will show you a bit later on a slide with inspiration what you could build with something like this. Of course, whole process of using text embedding model is a cycle that starts in the database. So you create a document in RavenDB or you modify existing one. This document will be pulled out of RavenDB. RavenDB will take it. It will send it to text embedding model. Text embedding model will produce vector. This vector will be returned to Raven, saved, and indexed. So when it comes to vector embeddings, situation is pretty much consistent as it is with other way of searching for data. RavenDB is still capable of automating lots of heavy work. Lots of heavy lifting will be automated. We try to encapsulate as much complexity as we could. So for starters, as you will see in a few moments, RavenDB is coming with one small text embedding model embedded. This is BG Micro V2, and it's producing 384 dimensional vectors. This is one model which is small enough to be embedded inside of the database. It's great for fast prototyping. It's not sending data outside of your database. Everything is happening within the database. And this is awesome for a quick start, for playing around with vector search, exploring what it can do for you, and to do some fast prototyping. Later on, if you go into production, if you want to do some more accurate searches, because BG Micro V2 is among models with lower accuracy, if you want to achieve higher accuracy, RavenDB supports you there as well with some of the external models, which we will see today. And not only that, there are some secondary aspects when you start doing implementations of communication with the text embedding model. There are some small details which are not obvious right away, but which are important. So first one is, whenever you have a distributed system, you have all these nice things, quotation mark, nice things happening, like unreliability of communication, latency. You will be paying for external models, so you want to be aware of what is going on. Also, you can already imagine if you have 1,000 numbers or 2,000 numbers for each phrase that you are encoding, over time, it will take space on the disk. So you also want to be mindful about disk allocation space. So today, text embedding models are not expensive anymore. They are rather cheap. So as you can see, a text embedding 3 large from OpenAI has a rather low cost. It's $0.013 for 1,000 tokens. A token is a term specific to AI, and you could say that the typical word that you will send to such model is being split into 2 to 3 tokens in most cases. But when you think about it, if you're implementing some kind of search, first you will have to compute embeddings for all the terms in your database, for all the words that you want to, text that you want to perform search on. And then every time that your user types something and sends to your database for matching, you'll also have to compute vector embeddings for the search term to be able to compare vector embedding for the search term and vector embedding from the database. So unpleasant part about this is that the more usage you have, the costs will go up. So you want to be mindful. One typical solution for this would be caching. So for search terms that are converted once, you would store that in some kind of cache or in the database. And then every time new search term comes in, you would first have to check if this is something you already computed a vector for. In that case, you will not have to make a call to OpenAI, of course, or any other model. Of course, you want to also handle the retries, because what may happen, not what may, what happens in distributed systems is unreliable communication. Also, I pulled out some statistics here. You can see it on the screen. Let's say you're using a text embedding 3 small model that has 1,536 dimensions. If you send 100 million terms and get back embeddings, it will take you half of terabyte, approximately, of disk space to store it. If you go with something more accurate, like text embedding 3 large, that has 3072 floating numbers in the vector, and you send same amount of data to be encoded into floats, you will allocate around 1 terabyte. So one of the solutions for handling such large disk allocation is called quantization. In RavenDB and in most implementations around the internet, you have 3 approaches to quantization. So something called single quantization literally means there is no change to the floats that are being returned by the text embedding model. What is being returned, you will store as it is. However, there are also 2 approaches called int8 and binary quantization, which are being used to shrink size of these floats, make them allocate less space, and you will have a trade-off. You will have smaller vectors, but you will lose some accuracy. So most commonly used solution is int8, which will take float 32 and convert it to int8. So what will happen is scaling factor will be applied. There won't be major changes in the vectors, so you could say their positions will relatively stay the same between 2 vectors, but they will be shrinked a bit. Precision will be lower. You will lose some accuracy, but this accuracy loss is moderate. It's bearable, and you will end up with 4 times smaller vectors. So you will allocate 4 times less space. So instead of 400 gigabytes, you will go with 100 gigabytes. Of course, quantization is necessary when you're handling a very large amount of data. And if amount of data goes really, really big, then you might decide to switch to binary quantization, which is actually very, very aggressive compression technique. So you can see it here. It will take an array of floats, and some kind of threshold will be established. And you will have binary determination if float number is above or below threshold. So as you can see here, 0.2 with threshold 0 is converted to 1, minus 0.5 is converted to 0, and that's basically it. So very, very aggressive compression, and you can already assume it's pretty much visible that you have high loss of accuracy. This operation means that you will end up with 32 times smaller vectors, so very, very aggressive caching. And it's extremely fast because now comparison between such binary vectors is very efficiently implemented to the extent that it's supported on most modern CPUs with vector instructions directly supported on the CPU level. By the way, if there are any questions, feel free to type them and I will answer them. And what I mentioned is, if you're looking for the inspiration, there are lots of scenarios, realistic scenarios that could be applied, where this could be applied and where vectors can help in implementation. So obviously, clustering is the first good candidate. Since you encoded words and phrases into vectors, now you're able to measure how far vectors are, and you can detect which of these vectors are pretty close to each other. So you can group items which are similar together. So you can go and say, this is summer equipment for beach. you would take something that's very characteristic for summer vacation, like beach towel and sunglasses, and you would represent them as a group and then compute vector embeddings for all other products and determine some kind of the threshold to create a cluster of products which are positioned in this highly dimensional space next to each other. By using such clustering, you can also detect emerging trends. Because if you follow searches in your product catalog and you compute vector embeddings for those search terms, you can detect what is now popular. Is there some kind of a trend? Also, you can use clustering to predict missing relationships. Because if you have something that is belonging close to a group, you can also determine what properties it will have. So missing properties or missing relationships could be detectable this way. Of course, something like recommendation system in e-commerce now becomes very, very simple and efficient to implement. Because looking at beach towel, I will be able to effortlessly offer similar related products on the screen, which is usually how people are shopping. So this will immediately benefit e-commerce websites. Also, anomaly detection is becoming much more feasible because you are now working with numbers. You're able to compute distributions, and then you're able to say, okay, this is my normal distribution, and my input that just arrived is far, far away from normal distribution. So I should pay more attention to this. So for example, if you have some typical scenario of processing credit card payments and you have attributes, time of the day, location, etc., you could say, okay, I'm going to compute a distance from one payment to another, physical payment to another, and I want to detect unusual patterns. One more scenario could be content deduplication. If you're not working with strict, exact data, if you can allow some inaccuracy, you can, for example, compute vector for every item in your database and then determine which one of these vectors are over, let's say, 98% or 99%. So you could offer one instead of the other. Maybe this could be replacement product, for example. Also, various kinds of examining behavior, which is leaving numerical trace, attribute trace, could be applied to profile user to better determine a model of their behavior and to, of course, ethically, and to offer them services or something else that would be highly customized to their needs and their behavior. So, enough slides. Let me show you one possible example of application of vector search. This is my Raven database, and you probably saw this. This is our famous Northwind sample dataset. I don't know if you ever read history of this sample dataset, but this is something that Microsoft created a couple of decades ago. This is database representing a fictional company that is trading food across the world. So getting food from suppliers, employees are selling products, orders are being created. Other companies, so this is wholesale, food is divided into categories, companies are purchasing, and then Northwind, which is the name of the company, is using shippers to ship these products. So now let's imagine simple task of creating a website that would expose these products. This is usual marketing strategy of many companies, besides their core business, they are building something on the edge. So what I have here is a small sample website with all these products. Let me show you how one of them looks like. A very simple model. So we have a name. We have here identifiers of the supplier and the category, quantity per unit, etc., etc. So you can see for each one of these products, we have that visualized on a card. So my task here is to implement something that we would dare to say, or we would dare to call intelligent search. So if I go and say something sweet, you can see results are decent. I'm getting something that is obviously good result. I must admit, I'm not too familiar with this, but this also sounds like a cake, French cake. This looks like some kind of syrup. I will have to check what this is, but this is packed in jars, so it's a good chance this is good match. Or if I go with German food, gummy bears. I'm not sure this, yeah, this is German. This is not sweet, but it's German. This as well, Frankfurter sausage, so results are decent. As you can see, I'm able to type in word German, and I'm getting back products which are obviously, well, most of them, obviously German one, but the word German itself is not appearing anywhere in the name. Or if I go with Italian, you can again see results are decent. Let me see with seafood. Okay. But what is interesting now, what happens behind the scene? Every time I send a word like this, it will be converted into vector, and a vector for this word will be compared with vector computed for this phrase and this phrase and this phrase. So what this means? Well, as you will see, I'm using a very good text embedding model, which is multilingual. And there's a hint here that this Explorer is multilingual Explorer, which means that I'm now able to offer right away, out of the box, without even thinking, multilingual search. So my colleague Grazian helped me. Thank you, Grazian. I have some Polish words here. I would not even dare to read them aloud, but I have translations here, so we will see how good search is. So I'm looking for something sweet in Polish. And as you can see right away, I'm getting something that looks pretty much convincing as a good set of results. Actually, it's excellent. Let's try with something that says meals from the sea. Or seafood, that would be seafood. Not bad, even though I need to, yeah, this one is good. I need to check all these dishes. Are they actually seafood? Maybe someone can help me with that. And let's see any meat pies in our catalog. Well, some of these are definitely looking good, even though I think this is sweet. The thing here is, these results are not perfect for the reason of not enough of a context. How this could be improved? Well, in this case, something like this or something like this is a dish. So if we would include recipe or short description, and then include this description into generation of text embeddings, what would be returned to us would be much, much more semantically substantial, and my search results would be even better. So this is not some kind of magic. This is me thinking how I can provide more information so that text embedding model has more material to work with. So how much code I had to write for something like that to implement? So searching over product titles, supporting multi-language scenario. Here is the code, and we will share this on the GitHub, so anyone will be able to clone this repo and run it on your own and play around with it. Actually, it turns out a relatively small amount of code. So I will walk you through the complete application and you will see how easy it is. So the first thing I need to do, I need to initialize my database, or I need to initialize document store, which is abstraction of Raven cluster. So here is the name of the database that I'm going to be using. And this is information about the server where this database is running. As you can see, it's my local installation running on my machine. When application starts, we are ensuring the database exists. So if database with this name is not existing, what will happen is we will send command to the database to create new to RavenDB cluster to create new database with the name that we set up. And that's basically it. Database is initialized. What you can see here, this is a class that is modeling product. When I say product, I'm speaking about these products. So you can what you can see here, this JSON, of course, is closely matching fields in this class. Again, this is great because I don't need two models. This is NoSQL database. Just a single business domain model is needed, and database knows how to store it. And finally, I have input field for search. What happens when I populate text here? As you can see, I'm typing, and as I'm typing, I'm getting results back. Here it is. What you can see here is the gist of this code. This is vector search directly supported on the syntax level from Raven query language. And of course, it's quite human readable. From products, I'm doing vector search, embeddings from the name. And please ignore this part for now. I will explain to you in a moment what this is. And what you can see here, this is, let's say, precision. So this is precision with which results will be matched and eliminated. This is threshold for returning results. Depending on the content in the database and on some empirical testing, I could tweak this factor here, which would be changing cutoff point for the products which are returned to me. So when I enter search term on the form, this search term will be sent along with this Raven query to the database. And here is how you do it. Session.advance, row query, because we are going to type it on our own. And this is the parameter which search term which will be replace here. So all of this is going to be sent over the wire to the Raven database. The Raven database will perform vector search, find matching products, and return them back into this strongly typed list of products. And that's basically it. If we don't have anything in the search box in the beginning, what will happen is that we will, simply speaking, pull all the products from the products collection or all documents from the product collection, deserialize them into strongly typed objects, and show them on the screen. And this is it. Essentially, these two lines of code is everything you need to perform vector similarity search between the search term your user types into the search box and the database. Now you remember the slide that says secondary factors. Obviously, it's not this simple. So let me now show you what is happening under the hood, what is the amount of complexity we try to encapsulate, and what are all the answers you don't have to search for. So in order to make this code working in my application, I had to do some relatively simple preparation. So first, I'm not using internal built-in text embedding model. I'm using OpenAI model. So what I did, I created connection string. As you can see, RavenDB has connector for OpenAI. I populated my API key here. I'm hitting this endpoint. And this is the name of the model on the API, on the OpenAI that I'm going to use. So once defined, this will remain here, and this will provide a way for RavenDB to connect to OpenAI text embedding 3 large. And when you look at this dialog for connecting to external systems, you can see that in version 7, RavenDB supports communication with Azure OpenAI, Google AI, Hugging Face, Ollama, OpenAI, of course, which I'm using today, and Mistral AI. This last model, BG Micro V2, is embedded one. So what is also nice, you can again build everything with the connector pointing to embedded model, test everything out, and then just in production, switch to paid external service. So this is first simple step. There's just one more step. I need to create a task. So what this task will be doing is this loop. I need to create ETL that would react to any change in the database, send document or document fields to external text embedding model. If there's no response from text embedding model, repeat it back again. Text embedding model returns computed vector, and this vector is stored in the database. So here is AI task that I created. So what you can see here, I'm stating connection string that I'm using. I want to process all of my products. So here is the collection products. And here is my specification, which fields from the products I would like to send. So what you can see I'm doing here, I'm sending the name of the product. But if I had, for example, if this was a recipe book, besides the name of the recipe, I could also send instructions for preparations and maybe a list of ingredients. These additional information would increase accuracy of the computed vector that would be returned to me. What you can see here is that Raven natively supports various formats of the data. So for example, if I have HTML text for the recipe that would be displayed on the screen, I don't have to manually process it to strip it out of the HTML text. RavenDB can do this for me. If I'm using Markdown, same story. One less thing that I need to do. I don't have to do processing of Markdown or HTML anymore. RavenDB will perform that automatically. As you can see, since product name is a simple string, I'm just using splitting here. This is parameter maximum tokens per chunk. So again, what is happening here is that we try to encapsulate one more thing to come up with sensible default. So again, one more thing you don't have to think about or learn what this actually means if you don't want to. Further down here is the quantization setting. So RavenDB again supports single quantization, which is actually not altering the vector, or if I want to compress them and lose some accuracy and trade that off for less allocation of disk space, this will happen automatically, autonomously once I set this up. But again, this is one more thing that you don't have to do. And down here, as you can see, we have two caching options. So if I have product with specific name, embedding will be computed for it. If I delete it and recreate it 5 days after that with the same product name, vector that would be computed would be exactly the same. But RavenDB is again natively supporting cache for embeddings, and you can set expiration time. So in my case, if I recreate the product after 5 days, there won't be any calls to OpenAI in my case because vector will be located in the cache. Same thing goes for querying, because when you type seafood, first we need to compute vector for it. Well, in this case, for 14 days, all vector embeddings for all search terms will be computed and stored inside of a database. And when you look at the documents, you can see at collections, you can see two new system collections that will be produced. As you can see, OpenAI large, you remember that was the name of my AI task. So this identifier of the AI task is used for new system collection that will be created with the field. Here how it looks like. So actually, when you look at this diagram, a vector is being returned and saved internally inside of the database, and this collection is exposing connection between the document and internally stored vector embedding. So what you can see here is the attachment, and I probably don't have anything to open, so you can try it and see how it looks like. So this is actual embedding returned by the OpenAI. So all of these things are encapsulated, lots of decisions that you don't have to make. And in the end, it comes down to setting things up once with the connection string pointing to external text embedding model, defining this task where I essentially had to pick up connection string, pick up collection, and determine which field from products is going, And those are all decisions I had to make. After that, I'm executing something like this, and now the meaning of this is becoming clear. So this vector search filtering condition will actually take the name of the product. It will locate its vector embedding within OpenAI large. Here it is. So it will take that embedding. It will compute embedding for the search term that user typed into the browser, and it will perform comparison or distance measuring, and it will know what is similar, what should be returned. So as you can see, this is not trivial. Certain level of knowledge is required, but we are not forcing you to learn it right away in order to start playing and experimenting with this. With relatively simple set of steps, you can set everything up, start working, and later on, if you want or when you need, you can dive deeply into topics like quantization or maximum tokens per chunk, or you can try out different models. So you can create different connection strings to using different connectors to different models, try out, see what is happening. I hope this was interesting. I hope you learned something, at least something new today. And I hope you will try this and get back to us. Let us know how this works for you and what could be improved. I really do hope you'll start playing with it and we can hear from you how you like this feature and what could be added, what should be changed in your opinion. Are there any questions?
Thank you, Dejan, for hosting this incredible in-depth talk. We are very glad. There are many amazing examples and tons of knowledge given away for free. I didn't see any questions yet, so I think we can safely go off air. And if you have any questions to us, more specifically at Dejan, feel free to chat with us anytime on Discord. And if you are watching on YouTube currently, the link is in the description, so don't hesitate to join. So thank you, Dejan, once again, and I wish everyone a nice evening.
Thank you. Nice evening from me too.
Thank you. Bye.